All right. Well, this one's really loud. It's good to see you guys. And let's see. All right. So today we will cover clustering, and this is our first unsupervised learning method. So all of the methods previous have been supervised learning, okay? Supervised learning means you have answers that during your training process, you have answers so that you can do something like cross-validation, where you can compare, you make a prediction, you train your model, and after your model is trained, you can have that model make predictions on some of your existing data, and then you can compare it. Okay, so it's kind of like having to see, like, did I learn the material well? It's helpful to have a practice exam, right? Because you can try out the practice exam, and then you have the answers to the practice exam, and you can see if I got all of the practice exam answers correct, then I feel like I've learned the material well. Whereas if you get a lot of the practice answers wrong, you say, okay, these are the areas where we can improve. And that's what supervised learning is you have training data with answers, whether those answers are numbers and you're doing a regression problem, or whether those answers are categories and you're doing a classification problem. So, the existence of target values allows us to measure things like loss, the difference between the predicted and the target values, okay? Whereas what we're going to introduce today and look at this week will be unsupervised learning, okay? So in unsupervised learning, we don't have any target values, okay? And we're trying to search for structure within the input values alone. So it's kind of just like studying with no practice exam, and you just have to say, I hope I'm getting this right, okay? But it's a little bit, you have to kind of make up your own metrics to see how you're doing, and so we have these kind of broad applications of unsupervised learning. And one is clustering, and the other is dimension reduction. So, so as far as clustering goes, clustering would be grouping similar observations together. It's still a kind of a big deal of getting clustering right. Clustering is basically what powers all of our recommendation systems. So, you go on YouTube, you watch a couple videos, right? If you go on like a brand new account, or if you're not signed in, as soon as you watch a few videos, it starts recommending other things, right? TikTok has a good kind of quote algorithm where it continues to give you content that you might be interested in. Netflix, all of these things that are, quote, have been successful as far as, being, quote, addictive, have very successful clustering algorithms as far as the content. So as soon as the user begins engaging with some content, they're able to then push more content that is, clustered similar to do that, right? And we don't necessarily have answers. They are looking for answers by kind of like, you have the feedback buttons of like, do I like this or do I not like this? And, and that kind of helps provide that. And, I guess goes into the reinforcement learning engines and stuff. But anyway, at the base, we have clustering. And the goal of clustering is to kind of group objects that are similar to each other, and then separate groups that are different from each other. And if you have features, then then you can start doing this, right? And so there's lots of ways we can define similarity, a lot of ways to perform the grouping. And yeah, so the first method we'll use for clustering is going to be kind of the simplest of these algorithms, and this is k-means clustering, okay? K-means clustering is a simple clustering algorithm. It's going to define objects as being similar by using Euclidean distance. So kind of like all the other things that use Euclidean distance, you know, and I didn't put them all in this slide deck, but things like, okay, you need numeric features, okay, because distance requires basically numbers, so categorical things are a lot harder to deal with. And then, and you should scale them so they're all on similar scales, because if you have one measurement that's like way bigger, then that's going to dominate all of your distance metrics. I didn't include that in these slides, but the principles that apply to Euclidean distance apply here. Now, k-means clustering, you know, it sounds similar to k nearest neighbors because they both have k's and they both use Euclidean distance. But it's important to remember that they're very different. K nearest neighbors is a classification method. It is supervised. K-means is unsupervised, okay? It's unsupervised and it's clustering, okay? K-means is going to be an iterative thing, okay? We're going to iterate before we settle on our answers. K nearest neighbors, there's no iteration. It just kind of, and there's not even a training process, really. You just take all the training data and then you just measure distances there, okay? But anyway, in k-means clustering, our clusters are defined by our centroids. And the centroid is basically just the center or the mean of the points assigned to a particular cluster. So this is just fancy way of saying take the means that belong to cluster of the points that belong to cluster K. Okay, so we have an indicator variable that's a 0 or a 1. 0 if it's not in the cluster, 1 if it's in the cluster. And basically, you are going to multiply that vector of zeros and ones by x, and so only the points that belong to that cluster will get added, and then you're going to divide by the sum of the z's, so you're going to divide by basically the number of points in that cluster. So this is just symbolically how we would calculate the mean of the points that belong to the cluster, but yeah, we use it with this formula with the z's. Okay, so this is how the algorithm works. And the first part is, first you have to decide how many clusters you will search for. This is a non-trivial problem, but you know, once you've decided how many clusters you're going to search for, then you start with some random assignment process. Okay, now there are different starting methods. Here I say randomly assign your points to some of the clusters, and then other algorithms will say randomly start with clusters. Okay, it doesn't matter. It's kind of a chicken and an egg problem. So in this one, we're starting with random assignment of points, and others will say start with random locations of clusters. But anyway, once you have the random assignment of points, then you're going to calculate your centroids. So you'll say, okay, these are all of the points that belong to cluster A. What is the centroid of cluster A? These are all the points that belong to cluster B. What is the centroid of cluster B? So on and so forth. Once you calculate the centroids, you reassign the points. And then once you reassign the points, you recalculate your centroids, recalculate your centroids, reassign the points. And you iterate back and forth between reassigning points and recalculating centroids. To reassign the points, you measure the distance from each point to all of the other clusters, or all of the other centroids, and you assign the point to the nearest centroid. So you're going to, whichever centroid is the closest, that is the group you get assigned to. Okay, so it's kind of, just imagine, I don't know, you're out on a playground or not, maybe not a playground, like a big grassy field, and you're playing some kind of games, and there's a whole bunch of people, and then they've got different flags or something, and you just say, hey, go to the flag that's closest to you, and that's basically how it goes. All right, and then we kind of reassign, move the flags around, and if you move the flags around, then which flag is closest to you will change. Okay, so we will. All right. So this is the alternative initialization method, and so this one randomly chooses initial centroids. So you have points, and you just randomly select some of these, k of these, however many clusters you're going to do, as the initial centroids, and then you proceed to do the same thing, reassign the values, recalculate the centroids. Okay. Oh, I guess I did include the slide, I forgot. So they use Euclidean distance. It's recommend to normalize or scale so they have similar values. Okay. All right, so this is a toy example, and I have 8 points, 0, 0, 0, 1, 1, 0, 1, 1, and then 3, 3, 4, 3, 4, 4, 3, 4, whatever, right? And so visually, if I said, hey, we want to look for 2 clusters, just visually, it's very easy. We'd say, okay, we have a cluster of points up here and a cluster of points down here, okay? And this is very easy for us to do, especially because our eyes and our brains are accustomed to looking at points in 2-dimensional space and 3-dimensional space. So we can do this very easily. But in much higher dimensions, like if you have points in 16-dimensional space or something, it's a lot harder to visualize. So, we would have to apply a clustering algorithm like this. Okay, but anyway, we'll go ahead and do this, and you will see that the k-means clustering indeed will identify 2 clusters of points. So we are going to start by just randomly assigning points to a cluster. So I'm going to say we're going to search for 2 clusters. I'm going to just randomly assign some points to cluster 1 and some points to cluster 2. So I just sample 1 and 2, and I'm going to do 8 values, and then I'm going to create my 2 vectors of 0s and 1s for the points that belong to cluster 1 and the points that belong to cluster 2. And I don't know if you guys can see this. Can you see the colors? It's a little bit hard. There are 5 points in red and 3 points in black. Okay, those are our 2 clusters. And so that's just random assignment, and it's fine. It's fine that we don't have 4 and 4. It's fine that you have an uneven number of points in each cluster. The only time where this can become a problem is if by random assignment none of the points get assigned to a cluster. Like if all 8 points ended up in cluster 1 or something, then you'd want to re-roll your initial assignment so that you don't, one of the clusters just doesn't disappear. It's more of a problem if you have like a whole bunch of clusters. If you're searching for 10 clusters, then you run the risk that like only 9 of the clusters end up with points and stuff. But anyway, this is what we have. We have 2 initial clusters, or 2 initial sets of points, 5 in red and 2 in black, and we will calculate the centroid of each of these things. Okay, so the 3 points in black are 0, 0, 1, 1, and 4, 4. Okay, and so that is going to be cluster 1. So 0, 0, 1, 1, and 4, 4. And so I'm going to say, okay, what is the mean of the points in X1 for cluster 1? So we're going to do 0, 1, and 4. The average of those is 1.667. And then I guess it's because it's 0, 0, 0, 1, 1, and 4, 4. We get 1.667 and 1.667. For cluster 2, looking at the points assigned to cluster 2, we have 0, 1, 3, 3, and 4 for X1, and then for X2 we have 1, 0, 3, 4, 3. Okay, and the mean of those points are 2.2, comma 2.2. So I'm going to go ahead and plot those. You can also use dplyr and just say, hey, group by your assignment and calculate the mean of X1 and X2, and that's what we have. And so this is going to be the mean of cluster 1 in black, and this is the mean or the centroid of cluster 2 in red. So this is 1.67, 1.67, and this is 2.2, 2.2. All right, well, let me give you your first view quiz answer, which is the letter A. A as in apple. A as in apple. Okay, and then so we go through every single point, and we say, hey, which centroid is closer? So for this point, I measure the distance from 0, 0 to this one and to this centroid, and I say, okay, this centroid is closer, so we're going to assign this to cluster 1. And then from this point, I measure the distance to centroid for cluster 1 and the centroid for cluster 2. We say the centroid for cluster 1 is closer, and we do this for all of our points, okay? So again, now that I'm over here, I'm going to say, all right, which centroid is closer? And so for this point up here, the centroid for cluster 2 is closer than the centroid for cluster 1, so it gets assigned to cluster. All right, so this is after reassignment. These 4 points have been assigned to cluster 1, and these 4 points have been assigned to cluster 2. And then now that we've assigned all of the points to the nearest centroid, we will recalculate the centroids. So I say, okay, what is the center of these 4 points? And it's going to be 0.5, 0.5. What's the center of these 4 points? 3.5, 3.5. And then so I plot those, okay? And then I go through and I would check which centroid is closest, and obviously, you know, we would measure the distance from here to here and the distance from there to there, and we'd say, okay, these points are all assigned to, will remain assigned to this cluster, and these will remain assigned to this cluster. So no points go through any kind of reassignment process, and so we will say this is converged. Okay. All right, here is just a slightly more complex example, and so here I have generated data from 3 clusters, okay, and I've got a red cluster, a black cluster, and a green cluster here, and I've just generated these points randomly, but when they come in, they're going to come in completely unlabeled. And when we do our algorithm, our first step is just random assignment of points. So all of our points come in unlabeled. We have no idea which, what labels or what clusters they belong to. And so I'm going to just randomly assign each point to one of 3 clusters. I'm going to just say I'm going to search for 3 clusters. And so when I do this, I got points randomly assigned to red, points randomly assigned to black, points randomly assigned to green. And then based on all of the points that are currently assigned to red, I'm going to say, what's the centroid of those? Based on all the points currently assigned to black, what's the centroid of those? And so on and so forth. So I can just calculate the means of these things, and I can plot them. And it's hard to see, but just behind, so I think the ordering of the plotting of the points is black gets plotted first, then red, then green. And the black and the red centroids are like very, very close to each other, and so the red centroid almost completely overlaps the black centroid, but they're right there next to each other. And then we ask, where's my stick here? We ask which centroid is the closest one. Okay, so for every single point, we go through and we say, okay, all right, so if I pick this point, which centroid is the closest, and we'll say, okay, the green centroid is the closest, right? The black one is just a tiny bit further away, and then the red one is just an even tiny bit further away, okay? And then if we're looking at points on this side, like this point over here, which one's the closest? The red centroid is going to be the closest. The black one is just a touch farther away. The green one is even a little bit more farther away. And so what we're going to end up seeing is kind of a split between red and green here. And then there's only like just a couple of points that would like this one right in the middle right here. And we say, hey, what's the distance from here to red, or the distance from here to black, and the distance from here to green? This one will probably, I just ran out of battery, get assigned to the black cluster. So after reassignment, this is what we see. So basically all of the points over here get assigned to green, all of the points over here get assigned to red, and then just a handful of points get assigned to black. And that's what we have there. Okay, and then once we have all of these points reassigned, we recalculate the centroid. So we say, all right, here's a whole bunch of red points. Where is the center of all of these red points? Probably somewhere around here. Where's the center of all of these green points? Probably somewhere around here. Okay, and then where's the center of the points in black? I don't know, somewhere around here-ish. Okay, and yeah, that's what we have. So these are the new centroids. And then now, again, we are going to reassign. And so this part is kind of more interesting. Basically, like between the centroid in black and the centroid in green, I kind of take the halfway point here, and if I split it like this, basically these ones are all closer to green, and these ones are all closer to black. All right, and similarly, let's see, look at this. I take the halfway point, probably something kind of perpendicular to that. These ones probably all closer to black. These ones are all closer to red, and that's how we'll see the reassignment there. So just imagine some kind of line there, and then so if I go, then that's what ends up happening. So we reassign the points, which centroid is the closest, and that's what we have. And then now that the points have been reassigned, we recalculate the centroid, okay? And we do that, and we just go through this process of back and forth between reassigning points, recalculating centroids, reassign points, recalculate centroids. And we keep doing this until nothing gets reassigned, okay? And so so this just a small change there, we recalculate another small change, okay? A few more points get reassigned. So you can see at this point, we're making very small changes here. And then at this point, I think nothing changed when I reassigned the points. And so that means we've converged. Okay, so at the point when everything is stable, nothing gets reassigned, nothing moves around, then we've reached convergence. And we can do a comparison between kind of the original clusters. So this was, again, I generated data from some multivariate normal thing. And so, when you generate data, sometimes you get a point, like this red point out here ended up kind of far away, and then this point in black ended up here kind of far away. And, compared to the assignments, this one got reassigned to the black cluster because it's closer, and I think that one got reassigned to the red cluster but again, we're just clustering based on distance, okay? There is a function in R called k-means, and it performs k-means clustering, and I ran it, and this is what it came up with. Now, the way it colored these points is different, but that doesn't matter, okay? It's like calling, if you have the same three groups, and one person labeled this one group 1, and that one group 2, and that one group 3, all right? That's one way to do it. And then someone else comes in, they're using the same groups, but they just labeled them different. Group A, group B, group C, okay? The label issue is, it's fine, okay? And so, there's kind of, you might want to look, so again, you don't really have answers to compare to, but we're always looking for some way to say, like, did I do a good job? And so you might try to do some kind of like confusion matrix between different, like if you run the same thing, do you arrive at the same results? And you're not going to get something down the diagonal, but you might still find kind of everything that was in group 1 the first time is now in group 2 the second time, but that still reflects that the clustering arrived at the same point, right? Basically, all of these points in red over here, just all of them became green, okay? And all of these points in green over here became red over here. So it's just kind of a label switching issue, and it's a very simple command, right? You just take your data and you call k-means on it. I'm looking for 3 clusters. It's one line. And then if you want to plot the results, you can say, hey, plot the data and then color them using results $cluster. And that will do it, okay? K-means itself, what it's doing is it's trying to minimize the within group sum of squares, okay? So the within group sum of squares is basically if I measured the Euclidean distance from every single point, let's say assigned to the red cluster, what is the distance to the red centroid, okay? So we're doing kind of a sum of squares, and so you can kind of think of like, these are like the residuals or whatever, and you're doing your within group sum of squares, compared to the between group sum of squares, which is basically, we would calculate maybe like the grand centroid, like the centroid of all of the points all together, and we're gonna say how different is each group centroid from the grand centroid. Have you guys taken 101B and with ANOVA? And so like in one-way ANOVA, you have kind of like sum of squares between groups and sum of squares residuals or sum of squares within. And it's kind of like that, but just now extended to a higher dimensional setting. All right, and so anyway, your total sum of squares is your within sum of squares plus your between sum of squares, and K-means is trying to minimize the within sum of squares. And so just like ANOVA and just like regression, if you add more terms and you make your things more complicated, you can always kind of shrink down your within sum of squares. But, you know, how many clusters is too many clusters? All right, let me give you your second view quiz answer, which is the letter B. B as in bear. Okay, the output of K-means is, you know, a list. It gives you the centroids, also the vector of who got clustered where, and then it calculates, you know, your between sum of squares divided by your total sum of squares, which is akin to like an R-squared value in ANOVA or regression. It's kind of you have the model sum of squares, which is basically the between sum of squares, divided by the total sum of squares, which is kind of like how you would calculate R-squared. And here we have 86.2%, okay? You can try other things, and you can say like, okay, what if I'm only searching for 2 clusters, okay? So if I just do K equal to 2, then I don't want to call it an R-squared value, but whatever this between sum of squares divided by total sum of squares drops down to 69.6. We can look at the results, and you know, this kind of makes sense. It just splits it into 2 clusters. It says this is one cluster and this is another cluster, okay? You can also say like, what if I wanted to look for 4 clusters? This is the issue of how many clusters do I search for? This is it's a hard question, because you can always like increase this number, right? By adding more and more clusters to search for. And it's tricky. Did I write a slide to this? Okay, so the comparison is kind of like on the census form. How many, and you can pick out like, you know, what is your race or ethnicity? How many races and ethnicities are there? And this is like an impossible question to answer, okay? Because, you know, if you go back, you know, a century, or I don't know, I don't even know when they started tracking race, but, you know, you go back a long, you know, decades or, you know, a century, you know, the census form would have only had like, is someone white versus non-white, okay? And then they realize, okay, well, maybe we need to have more than that. And then, so you'd have maybe, and so then you might have white versus black or of African descent, and then maybe American Native or Indian, Asian, Hispanic, Latino, you know, and it's complicated, right? You have white non-Hispanic, and you know, white Hispanic and things like that. And then you know, I'm Asian, and so even among Asian, that can get further divided into, East Asian, South Asian, Southeast Asian, Central Asian, and East Asian can get further divided into, Chinese, Japanese, Korean, things like that, right? And you can keep finding more and more groups, and yes, every time you do that, you will bump up this quantity of between sum of squares divided by total sum of squares. And the question is, well, yes, I am identifying smaller clusters. Is there a point where we're not making that much of an improvement? And again, it's kind of this impossible question to answer just simply based on the numbers alone. And you probably want to incorporate any kind of domain knowledge that you have, okay? One issue that might point out that you might be looking for the wrong number of clusters is that if you run, say, k-means clustering with k equal to 4, this is one possible clustering. So we have a blue cluster, a red cluster, a black cluster, a green cluster over here. But depending on the random assignments I have at the beginning, if I run this again, I get, a different split. So this one, basically the points in the middle, like these ones look like they are stable, but the points in the middle can kind of end up split like that or like that. And here's another one. These ones, identified clusters over here, it split them and things like that. So the results, if you're getting like different results every single time, it might indicate like, okay, maybe this is not the correct number of clusters. When your clusters are very kind of stable over every single thing, that's a good sign. And so these are indications of things that perhaps you might have the quote right number of clusters, but even then, the quote right choice of k may not necessarily result in all of the runs of k nearest neighbors converging to the same results. It's a tough question. How many clusters to search for is always kind of hard, right? And again, it's difficult to know. Here's just kind of a thing that I tried running where I said, I'm going to search for 2 clusters 20 different times. I'm going to search for 3 clusters 20 different times, 4 clusters 20 different times, 5 clusters 20 different times. And I just kind of wanted to, every time I run k nearest neighbors, I wanted to look at the within sum of squares and see if that stays stable or if there's kind of variation. And so some of these results, every time I ran it with two clusters, the within sum of squares is exactly the same, meaning it arrived at the exact same results, okay? When I ran it with three clusters, you can see the within sum of squares ends up exactly the same, indicating like they always converged to the same answers, okay? But then when you're looking at, say, like 9 clusters or 10 clusters, the within sum of squares, bounces around a little bit. Sometimes it converged to 343, which is quite high. Other times it ended up, less at 254. With 10 sum of squares, as high as 306, as low as 232, or I don't know if there's something lower than that. And so, you get different results. Okay, and so I just said, hey, give me the average, and let's plot these. And this is what we see. So with 2 and 3, no kind of fluctuations. But when we're searching for k equal to 4, 5, 6, 7, 8, 9, you can see as I increase the number of k, my kind of quote, like the within sum of squares, which is akin to your residual sum of squares, continues to decrease. But we do see, the estimates are not as stable. So probably searching for 3 clusters would be the right. But, it's, again, not always going to be clear. And this kind of analysis is computationally expensive in that I had to run k nearest neighbors 200 times, right? I ran it with 10 k equal to 10, 20 times to see what kind of values I get and things like that. So So anyway, that's kind of our introduction to k-nearest neighbors. Just running quickly through it. I give you 2 answers? Okay. Third answer today is the letter C. C as in cat. Okay, so we'll wrap things up here. And we'll see you guys on Friday. Yeah.